All right.
So good evening, folks. This is Mupala Sridhar. Today I'll be giving a presentation on Fastrack, Fast IO for secure machine learning using GPU keys. So agenda for today's presentation, initially I will be covering the introduction, followed by showing the baseline performance numbers, the latency numbers, and then the implementation details to reduce the latency as is being covered in the fast track design, and the results of the fast track are covered in the evaluation, and there is a conclusion like what has been achieved. And if you have any questions, please interrupt me. I will try to answer your questions. The source of this content is from the paper that is being shown in this slide. And the authors of this paper are from USC. They are like PhD students. You see their names here. They have completed this paper under the guidance of Professor Dr. Murali Annavaram. The students have worked on this project for almost 9 months. Close to 3,000 hours were spent to come up with this beautiful and excellent paper. Terminology that I'll be using in today's presentation is the T, the trusted execution environment. So it is a secure area within a main processor that ensures the execution of code and the handling of data in a trusted manner, uh, protecting it from outside interference or unauthorized access. So this is a new thing that has been coming up. Yeah, CPU Ts have been there for a long time, but the GPU Ts are the ones that are coming up because like the customers are asking for secure transaction in each and every part of the workflow, not just only on the networking side, but like within the CPU and GPU, they want like all the data that is being processed within the CPU as well as the GPU. They're all like secure and isolated. They don't want outside interference to come into picture. And like I think for this paper, they have used Intel Xeon Gold 6548 Y plus processor they have used, and 512 gigabytes of DRAM memory has been used in the CPU-T. And like the GPU-T, NVIDIA H100 has been used. So NVIDIA has been shipping the T features uh, from like a Hopper architecture, the H100, H200s, and even in the Blackwell, they are supporting the T features, the GPU-T. So the older GPU cards that were shipped from NVIDIA, like A100, A2s, and all this stuff, they don't have the T support. Okay, and like they have used the AES GCM for encryption as well as authentication. They have picked up 256 bit key, and like I'll be using the terminology AD MAC, which is used for authentication purposes, like data integrity. So I'll be covering those things in the upcoming slides. In some cases, like I'll be showing the paper also. The introduction here in this diagram, like you see, like there are two major components: a remote user and a cloud server. And within the cloud server, you have two components: CPU T and GPU T. And here you see they're all securely connected. The remote user is connected to the CPU T and using the secure channel, and like they use this blue color shade key. The blue color shade key is used between the remote user, and the CPUT. And the communication between the CPUT and GPUT is also secure, and they use the shared key. Here it is a yellow key. Two separate keys are used. One for communication between the remote user. Remote user is none other than like it could be you, like working on a laptop, like from your browser you are trying to connect. Okay, so like that's where like the shared key is used between the remote user and the CPUT. And like this another shared key that is generated between the CPT and GPT. Uh, Again, like it is used uh, for secure communication between the CPT and GPT. Okay. And like with respect to inference, okay, so again the same diagram, but like more details I'll be sharing. So the remote user, again, like they will be using a shared key between the CPU and the remote user, and the yellow key is used between uh, the CPUT and the GPUT. So how is this shared key that is being used between the remote user and the CPT comes into picture? So like if you look at like uh, end user, typically like they will end up uh, using a TLS protocol to establish this secure connection. So the TLS protocol involves like first the TCP three-way handshake has to be established between the remote user and the CPT here. Like there is a process which will be running on top of CPUT. That's the one which will be communicating with the remote user. And once the TCP three-way handshake is established, then like TLS connection is established. In the TLS connection, that's where the shared key is generated. So I think either they can use, I think like they can use the uh, private public key kind of operation, and like eventually using that operation, they'll end up generating a shared key that will be used both by the remote user and the CPT process which is running on the CPT. Okay. And like there is another key that is generated between the GPT and the CPT. And again, like these keys are specific to a specific session. If there are multiple users, they'll end up using different keys, like the shared key is unique, the blue shared key is unique, and the yellow key is also unique. Okay. So what is happening is any data that is sent by the remote user that is encrypted with this blue colored shared key, and it is sent to the CPUT within the cloud server, and the CPUT application process will decrypt uh, the packet, and then like what it does is it encrypts the, I think first thing is it checks like authenticity of the received packet. Plus, once it is all verified, then it encrypts the data with this uh, yellow colored key, the shared key between the CPT and GPT. And this one will be sent to the GPT, and the GPT will decrypt it, and then like does the processing of that packet, whatever the information, the data has been received by the GPT, and like after it processes, typically it processes it either on the uh, tensor cores or on the CUDA cores, which are on the GPT. Once all this processing is done, it encrypts the data and like sends the data back to the CPT, and the CPT will decrypt it with the shared key and checks there is no foul play, and if nothing, then like it again encrypts the data with the shared key that is shared between the user and the CPT, the blue key, and it sends it back to the remote user, and the remote user decrypts it, and he sees the resulting data from here. So it could be an LLM which is running on this GPT, and the remote user is issuing a prompt, like a So they are connected to a chat GPT kind of application. And like this is path that can be established. I'm just giving an example. Uh, I think a lot of people are familiar with it. Like they issue a prompt, the prompt goes in a secure way to the CPUT, and the CPUT sends it to GPT, and GPT after decrypting it, it runs that prompt on the LLM, and the LLM generates the data, I think nice text, and that is sent back to the CPUT, and CPUT decrypts it, and again it encrypts with the blue color shared key and sends it back to the end user. Any questions on this?
Hey, Sridhar, a quick question. Can you hear me, Sridhar?
Yeah.
Oh, this is a very good explanation. Thank you for that. So, just this is more implied, but just for clarification, for multiple users, is it presumed that you have multiple keys on that CPUT, or is it just one?
Oh no, there will be multiple keys.
Okay, good. That's what I was thinking. Good. Thanks for clarifying.
Any other questions? Okay, this is the inferencing one. And like this slide like explains all the steps that I just shared with you guys. And again, like the inferencing models, like in general, like we see like good amount of time is spent on data transfer, less amount of time is spent on the GPU processing. And when it comes to the training, so the data is already uploaded into the CPUT. All it does is it encrypts the data with this LO key and sends it to the GPUT. Okay, and like once the GPUT receives the encrypted packet, like it has to decrypt it and then does the processing of the received data. So mainly it has to train, like humongous amount of data keeps coming, and it has to be. So in training, a lot of time is spent in GPU. The reason is like it's all vector multiplications. So what happens is the vector, the huge matrix is divided into smaller chunks, and like they keep like sending the data to the memory, and like they fetch the newer subsection of that matrix. So there is a lot of time that is spent like computing, but also sending back to the memory. So all that stuff has to be yeah. So like that's why like you'll end up seeing a lot of time that is spent in GPU. But I think if you look at in general, like the GPU utilization is probably like 10 to 15% of the GPU resources are available. So like most of the time, like it keeps waiting, fetching the data from the memory, which is in the GPU itself. So if I look at like the way things are right now, are like similar to what was happening 25 years back. So back then, like Sun Microsystems servers were dominant in the enterprise market, or even the e-commerce sites. So many .com companies were popping up. So like I think like back then also there was no virtualization concept, like towards the end of 90s. All the servers were like I think they were adding a lot of servers, like a single OS was running, and like only 20% utilization was there, like of the CPU resources back then. Then like VMware came into picture, like they brought in the virtualization concept, and they came back and like they told, hey, like uh, so instead of running one OS on a single server, so we can run like four virtual machines, which equates to 80%, and 20% is kept as a buffer. So like so 80% of the CPU usage came into picture. But I think like industry has settled with 60%. Like in general now, like if you hear from anyone who is managing the data center, they say like 60% usage of CPU on a server is very good. They always want to keep some buffer. Okay. So now coming back to the GPU world, yeah, as I was telling, like I think the OpenAI or like Meta or all these guys, like they are building up clusters like 100,000 node clusters or even million. Like some places we are hearing like they are in the process of building a million node clusters. Okay, but like the GPU usage is only 15%. So yeah, I think NVIDIA has come up with this vGPUs as well as the MIG. So through MIG, like multi-tenant feature can be implemented where like they can physically dissect a, GPU into multiple hardware chunks, and each chunk can be assigned to one tenant. Okay. So, but in general, like I think there is a lot of work going on how folks can efficiently use the GP resources. Okay, uh, so this paper talks about how to efficiently improve. I think that from the optimization point of view, but I also gave you other examples, the MIG or like VGP is another one, like multiple VMs will end up sharing the same GPU instead of like only one VM being dedicated to particular GPU. So like these features, yeah, the MIG features are available in high-end GPU process like Hopper architecture as well as the Blackwell. So any questions on the training side? Okay, so this is the content that I just covered. So the baseline, yeah. So here you see like,
See,
yeah.
just one question I want to ask you. On the training side, when you ask that question, right? So when they do all these gradients and all these calculations across multiple GPUs during training, batch processing or what have you, that means before they do all that training, all these keys have to be established, uh, and then the data flows and the processing goes on, right?
Okay, so like I think, see, there are two things you are bringing up. The training is always done first. After the training is done, then the inferencing part comes into picture. So like whatever the training is done, like it will generate a model, a file, and like that's the file which needs to be loaded into uh, uh, the GPUs in the inferencing. So like no training goes on. So in the training model, that's where like a lot of that vector multiplications, like heavy compute operations are done. Uh, Less computational operations in the inferencing side. So
Yeah,
both
true.
are, yeah,
So
the
my,
training.
my question is that in the training phase also, do you need that keys exchange like you described here?
Yeah.
All these.
Yep. Yep. Yeah. This key is different in the training phase because they'll be running on a different servers. Okay. So these are massively core data center servers that they will be running, and like these are typically the edge servers, like in the inferencing phase. Okay. Because like you
Got
don't
it.
want to
Thanks.
send the remote user traffic to a core data center where like the GPUs, usually like low end GPUs are used here. So and also like what they do is like typically in the training model they may end up coming up with a 32-bit based LLM. But I think when they deploy the LLM on the edge, they do the quantization. They try to reduce it to I think like 8-bit or 4-bit, depending upon like how much memory that edge device can handle. So, but I think like there will be a penalty in terms of how accurate, because the more you reduce uh, the bits, Yeah, I think like you may not get the accurate results. But in general, yeah, they go for 8-bit. That should be fine, like to get most of the results in an accurate way. But I think like on top of this, they're also adding RAG so that like they get more accurate results.
Please read the question.
Yeah,
In the next slide that you had.
yeah,
You know, the question I'm having is the CPU T to the GPU T. Normally, that connect channel is a PCIe kind of interface, right?
yeah.
Server. What kind of attack vectors do you have to make sure that this needs to be protected? Secure channel. I understand it's TPM to T to T, but do you know within a server, within on the PCI bus, do you see attacks? Is that the reason why this needs to be protected?
Oh, no, no, no. See, I think like, see, if T is not used, see, like what happens if the data that is loaded into CPU, okay, it tries to, if it does, if there is no secure connection, okay. Uh, so like, even if there is a, see, like the key thing is the data that is loaded, it is put it in an enclave, okay. That is like the harder, the memory that is allocated for T, okay, no one else can touch that part of the memory, the physical memory. Okay. So anything that is stored uh, in that memory can only be accessed through this shared key. Okay. So like anything that goes on the bus, it is already encrypted with the shared key. If someone tries to sniff and copy and like then they want to decrypt it, yeah, but like they don't have access to the shared key, this shared key. Also stored in the that hardware enclave.
Agreed. The question I had is, you're saying the data is okay. So I think that's the part I was trying to understand. There's a secure channel, and the data is also kept encrypted. So you want to. My question is really, I'm trying to understand the need for the secure channel between the CPU and GPU where they're going on the PCI, and then you're saying there's a potential for attack there because
Yeah.
somebody else could snoop
Yeah,
on
yeah. The people can attack this part, or they, if someone hacks into OS, if they have access to the memory, then they will try to access the content of that memory also. But like
So,
hacker can come into the CPU, but he will not have access to the T stuff. The moment, like, yeah, because it can be only access to the secure this shared key.
got it. Good.
Okay.
Okay, thank you. And the last question before you go to the next slide, the GPU, you mentioned multi-tenancy with the GPU. All the networking interconnects like the InfiniBand, etc., they support virtualization as well. The kind networking GPU to GPU connection.
See, GPU to GPU communication within a server is done through NVLink. So NVLink,
That also, they
NVLink is
also,
the
yeah, my
NVLink.
question is they support virtualization also today, right?
Yeah,
They
just
also,
let me complete that part. So the NVLink is used for communicating between GPU T to GPU to another GPU. Okay, it is up to the end user how he wants to. I think like the NVIDIA provides libraries. It's up to them. Like if there is a communication that is needed between two different GPUs running on the same server, they have to use the right libraries for it to be secure. But like the T, like a T is not valid for communication between two GPUs. So it's NVIDIA which is providing, and people have to use that part. Okay, and like when you're talking about the InfiniBand technology, that is used for communication between two GPU servers. Okay, there they use RDMA for transferring the data between two GPUs which are located in two different servers. Okay.
got it.
Okay. So any other
If you don't mind, I thought there is an intra, there is inter also, right? What you said was inter between two servers, but even within a server, if you have multiple GPUs, they still go through InfiniBand and RDMA, isn't it?
No, they go through within the same server, the communication between two GPUs are done through NVLink. That is a proprietary technology that is developed by NVIDIA. It has been there. So like I think for each version, they keep bumping up the speed lines between the
True.
speed that is
No,
supported.
no.
Yeah, I think InfiniBand is only used.
No, I'm not disagreeing with that, but I'm also saying in addition to that,
Yeah, go ahead. I think we
your
lost you.
connection.
Yeah. Can you guys hear me?
No, you finish off. I think your last message got chopped off.
Okay. What I'm saying is, based on whatever information I have been gathering, so the GPUs within GPU server, okay, they use NVLink technology for communication purposes. InfiniBand switches are used for communication between two different GPU servers, the DGX, DGX server 1 to DGX server 2. For that, they use the InfiniBand. The GPUs, they can have 10, 15 GPUs within the same DGX. The communication between the GPUs within the DGX, they use the NVLink. So did I answer your question?
Okay.
Yeah, because I haven't heard.
You did answer. I thought for that also.
Yeah, I'm losing.
I thought for that also you'll have a GPU NIC for some custom cases where that'll also use the RDBMA to access the memory of the GPU to communicate, and InfiniBand technology or NVLink is what I thought.
Yeah, if you are using a NIC card, so that's what see, a GPU server to GPU server will end up using a NIC card. So that's where the RDMA comes into picture. But when the communication is between GPUs within the DGX server, there is no need of using a NIC card. Okay. And that's the beauty.
Great,
I
thanks.
think the other, I can cover a little bit on that part because I worked at Sun Microsystems. So we heavily invested in InfiniBand technology, and Sun has invested in Mellanox, which got acquired by NVIDIA. So what I see is the communication between two GPU servers, okay, using the InfiniBand technology, where the RDMA is used, and the guaranteed low latency is 100 nanoseconds, okay, compared to the Rocky, which is RDMA over Ethernet. The lowest they can provide right now is 200 nanoseconds. So especially with this LLM foundation models which are being created, that lower latency guaranteed one is a killer. So there is no competition for NVIDIA in that space. So that was the best acquisition they made. I think buying Mellanox, they have a huge advantage. So there is no competitor in the marketplace who can provide that 100 nanoseconds guaranteed low latency. So other competitors are coming up with servers, GPU servers, and they can communicate with each other through the Rocky, which is they use the Ethernet's technology. So it is lagging big time. So let me go through the baseline. Any other questions before I go to the baseline part?
I have a question. So where is the difference coming from performance? Is it because of the InfiniBand and Ethernet, or the technology itself is efficient for Mellanox?
Oh, I think InfiniBand is a connection-oriented protocol, and a lot of I think the protocol itself provides guaranteed low latency. So whereas Ethernet doesn't provide guaranteed low latency.
The point-to-point protocol, and it's not a best effort protocol like Ethernet.
Yeah. So and the other question is that why there is no competitor in the space. So only Mellanox produces the InfiniBand. There is no other player in this space.
Yeah, I think like as far as I know, there were like few startups which came up in early 2000. Okay, Cisco bought it and they killed those InfiniBand because Cisco did not want InfiniBand technology to exist because they wanted to use only Ethernet and promote Ethernet in the enterprise customer space. So I think like Mellanox was not interested in being acquired by Cisco. So like, and also Andy Bechtolsheim from Sun. So who was a co-founder of Sun? He's a big promoter of InfiniBand. So so like Sun has invested a lot of money in this technology, and like the result is like when Sun got acquired by Oracle, so like during the transition phase, we build like engineered systems. The engineered systems is nothing but like communication between the database servers and the storage servers going through InfiniBand switches. And there also they needed low latency, especially financial customers. They wanted guaranteed low latencies. So like that investment, like has paid off big time to Oracle. They make like $1 to $2 billion every year just on those engineered systems product line. And uh, but I think like a time came like when like I think like Mellanox was not growing, but then like they approached like I think looks like they approached Oracle and like also Nvidia. But NVIDIA, I think they proposed to NVIDIA like how their InfiniBand technology can be used for GPU server to GPU server communication, providing guaranteed low latency. The timing was very good. They knew like this stuff was, I think like more and more GPU resources are needed for creating the foundation models, and like providing a guaranteed low latencies will be a killer for them to provide that kind of solution to OpenAI, Meta, like Google's, or like Microsoft. Any of these guys were building the foundation models. But again, like when it comes to inferencing, like you don't need like that kind of GPU processing, edge devices. So a lot of startups are coming up in this space to target the inferencing market. And like the inferencing market is the one like where like Broadcom will also play a huge role. Like I think AI chips are coming up, targeting the edge AI compute. You see, that's the reason, like you see, like in the last few days, the Broadcom stock has gone up by almost $70.
And these are nothing but the XPUs, right? AI XPUs, correct?
You mean the edge AI? The edge AI chip?
Yeah, edge AI.
Yeah.
From Broadcom or the AI,
Yeah.
chip XPUs, right?
Yeah.
I see.
Yeah, I think they keep coming up with some new terminology, but I think I call it as edge AI based chips.
So
Okay.
there is something called NV switch, right? That is actually connecting the multiple servers, right? GPU servers. So that NV switch is actually talks the InfiniBand protocol to route the packets.
I think I'm not aware of the NV switch stuff. See, like InfiniBand switch is there, like which takes care of connecting to
I think
multiple.
that is becomes the NV. Isn't that the NV switch?
Yeah, maybe NVLink connects to the NV switch most probably.
Yeah, so I can just chime in a little bit to what I'm aware of that. So when the PCI buses from the GPU, when the data is sent, they either on the other side, they will either talk to the NV switch and then to the CPU and go to that memory. So that is the connection point to go through. And if you want to avoid that, then you can avoid that and go directly to the GPUs if you're going server to server. So it's there are two variations, intra and inter.
Yeah, okay.
And I think one other thing also I wanted to bring up on the topic that came up, right? So I think whereas I think Shankar, when you mentioned about Ethernet, I think the protocols handle um, the loss. They avoid the lossy network, right? Whereas if you're going with the RDMA, I think the network itself ensures, because it uses UDP, is my understanding. The network ensures to make sure that there is no loss of packets or anything.
That's because special wiring, right? Ethernet has a transport at the lowest level.
Exactly. The
It's the
TCP
best
and all
of
that.
it.
Yeah.
So they have to make sure the switches, how they wire it up, etc., lossless, and they have to have some special protocols like PFC or some additional, can call it QoS protocols to ensure no loss, right? Whereas
Right.
InfiniBand by design is a point-to-point protocol, right?
Right.
And therefore much better in performance, right? So
Right.
it is costly to buy an infinity band switch compared to an Ethernet switch. So there is
Yeah.
obviously you can't just like wholesale shift to Ethernet kind of infinity band switches, because that's like super expensive. So that's why the desperate thing to um, see if we can work with what is the low end or the medium end. Can we use Ethernet? That's why our ROC is popular, right? Because there's always value in reusing what you have.
Yeah, I think like there is a big learning curve for InfiniBand.
It's
Like,
also the cost to replace, right? It's just too expensive. So there's many data centers will love to reuse what they have. So Ethernet will find its lifetime. It will continue to, even though the trade-off is huge, 100 to 400 nanosecond that Sridhar was talking about. That from a latency point of view, the cost to replace Ethernet switch is very high.
yeah, I think the specific use cases only like it makes sense. But right now, like the foundation model is a very good use case for NVIDIA to keep selling. Yeah.
Okay.
Okay, so let's move on to the baseline. So yeah, this one like just the encryption, like how it is done. Like I think the input is split into multiple plain text. Like I think what you see is the plain text. Uh, so it is an operation with the shared key K1. Okay, the K1 is the shared key that is used for each and every text, and it generates a ciphertext. The key thing is this shared key. Okay, it is used in each and every operation. Only the plain text is keeps on changing, and it generates a new ciphertext. Okay, nonce is a unique number. It is generated again. It is same here. So in the so here, like if you look at like this one is all like this stuff can be done like parallelly. The encryption part like can always be done parallelly. All of each of these can be executed on uh, uh, a unique CUDA core. Okay, so parallelism is possible in the case of encryption, or even decryption. Also, you can do it parallelly. That's a beauty. So when it comes to MAC generation, here you see the ciphertext 0, like it goes through this subkey H, and then like the output of this stuff becomes, I think the output of the previous one is is fed along with the next ciphertext, and then like fed into this multi-sub key H. So you see like all this stuff is nothing but a sequential operation. So this is this slows down. Okay, and towards the end, yeah, nonce is added and you generate a MAC tag. So this is mainly for authentication purposes. Like MAC generation is a sequential operation. So you cannot take advantage of parallelism, even though like the GPU is providing. Okay. So actually they modified this part like as part of the Fastrack. They made it parallel. I think not parallel, but I think like, yeah, I'll tell you like what they have done, how they achieved the parallelism. So here, like the inferencing, as I was explaining earlier, so there is a decryption and the authentication part is uh, is executed on the CPUT after receiving the traffic from the user, and then like it takes care of encrypting and like generating a MAC. Okay, and sends it through the PCIe channel to the GPU, and the GPU takes care of decrypting and also checking whether the received content is not tampered. So that comes into authentication part. And once it decrypts, then it starts executing on the GPU, the inferencing part. Okay. So this is what happens. And then the reverse also same thing, like you end up encrypting, and then like you do the decryption here, and then like you again encrypt with the shared key with the end user and send it. So with respect to training, all you do is like encrypting and like generating the MAC and sending it in on the PCI bus, and like it will be received by the GPU, and the GPU will take care of decrypting and like also calculating whether the received content is not tampered. The authentication value should be matching. If everything is good, like then like it feeds into the GPU, the cores. So the tensor cores or the CUDA cores. Typically for vector multiplication, they'll end up using the tensor cores. If the tensor cores are not available, then like that vector multiplication is done on the CUDA cores. So the three models that they have used in the in this paper. So they have used ResNet 50, a vision model. Basically, they use the ImageNet data set, like it has like 14 million images. So yeah, here I think like in general, like the ResNet 50, yeah. So a lot of image related. I think like the other two models are the ones where like a good amount of time is spent in the data transfer. So you see like a lot of benefits in this, like the two-tower neural network and the graph stage, which is a graph convolution model. So in the two-tower neural network, like the movie lens 1 million data set was used. Okay. So here you see the data transfer time per batch. So here you see like ResNet, which involves image stuff. Here you see in this column, you see no GPU T, okay, for training. It took like 312.5 microseconds. And like this is like confidential computing, which is same as T, okay? So if you say GPU T or NVIDIA CC, they are like same. So NVIDIA calls it as confidential computing. So 3.96 millisecond is spent in the data transfer and like 6.41 milliseconds. The rest of the stuff, yeah, you see, let's compare this with the total execution time. In ResNet 50, you see like in no GPU T, 35.84 milliseconds are spent. If you compare that with this, so the data transfer is very less. Most of the time, ResNet 50, they end up spending in the GPU. Okay, so 34, I think almost like 35 milliseconds is spent. Same thing like NVIDIA CC, if you compare 39.49 milliseconds. If you look at this one, it is 3.96. Okay, this is the training one. If you look at the NVIDIA CC, the inference, the data transfer is 6.41 milliseconds. And if you compare this, yeah, there it looks reasonable, just like close to 3 times. Okay. But others are like huge difference. Okay. Yeah, I think the image part, the training, like it involves a lot of computation, that's why. But compared to other, like the other two models, you see, they spend like good amount of time in the data transfer. If you look at 2.1 milliseconds versus 8.6, so it's like 1/4. And then here you see NVIDIA's CC, the training model, like 32.6 millisecond is spent. Okay. And like here like 39.16. So the difference is only like close to 6 or 7. Yes, 7 milliseconds. That's all. Close to 7 milliseconds is the difference. But major chunk of the time is spent on the data transfer. Okay, so here also you see 45 to 48. So like when you look at the TTN, like here you see 51.43 versus here also, like you see good chunk is spent on the data transfer. So I think like wherever there is more data transfer, that's where like wherever the latency, good amount of latency is spent in the data transfer. So this particular Fastrack helps in cutting down that drastically. Okay.
So have they broken down the data transfer cost? Is it the encrypt, decrypt, or is it the transport? Or what is the, how is the breakdown
The
of the
transfer time, the transfer time, that's one
Yeah.
thing. Yeah. So even like, the encrypt, decrypt, there are double encryption in each path and
Okay, so that's a breakdown you're saying later.
yeah, there are three things, but I
Okay.
think in general, like,
I'll wait for it.
yeah, all three, but I think in one of the diagram, you'll see like how much, just by, for direct communication, how much they are able to get it down.
But is that the same thing also applies in inference part also, Sridhar? That's why you see 73.45
Yeah,
milliseconds.
that looks,
Yeah. See, this one 73.45. This is a data transfer time. Okay.
so
And
yeah,
the rest,
educate me on that inference. I just had to Raj question, if you don't mind, Raj. This inference, when this time is the transfer from the store that you. I'm trying to break down this in my mind. When you're doing the inferencing, where is the time is the way, where is the data? I mean, the data for actual user data must be very small, right? ChatGPT, a query or something like that.
yeah.
That can't be very that expensive, right? The transfer data transfer cost. So I'm trying to understand where the 73.4.
Yeah, a good chunk of the time is this encryption, the decryption and encryption. That's where that's
Of the user query, the user, because they're not transferring the entire
for impressing
model
it
data.
could be just a query or whatever, it could be an image that they are loading. So like good amount of, I think like if you look at the last, I think like the comparison slide, then you
Okay.
get these numbers
Okay,
will
we'll
pop
wait
up there also. Yeah. Okay.
Got this.
Okay. The Fastrack design. So like I think we are going back to the original diagram, remote user, the cloud server. So I think like uh, before the Fastrack is implemented, you see there is an encryption here, there is a decryption followed by another encryption, and then like there is decryption. So like there is in each path, in the transmit path, there are two encryptions and there are two decryptions, and also MAC calculations are also involved. Okay, and MAC calculation is all serialized. Okay, and then like even in the reverse path also you see two encryptions and two decryptions. Okay, so like they looked at this as inefficient, so they have cut down uh, the decryption and encryption in the CPUT. This was taken out, so the communication is going to be remote user with the GPT going through the CPUT. CPUT will just do a pass through. It will not do decryption. So they had to modify the code so that like they know like the the data that is coming from the remote user is encrypted. So it will not do any decryption. It just passes it to the GPU, and the GPU will use the shared key between the remote user and the GPU. Okay, that's the one which will be used for decrypting, and like then it does the processing, and then it again encrypts and sends it back to the remote user through the CPUT. Okay, so the way it works is like this guy, like when he sends the request, the remote user, like in their like Fastrack implementation, the code which is running here, they exactly know, because like already like the shared key between this GPUT and CPUT is already generated, and that is already stored in the CPUT, and the access to that is through the GPU driver. Okay, but like instead of GPU driver, they implemented their own uh, 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 emulation software, which takes care of having the shared key, and that shared key will be used for, I think it will just pass through and like, because it knows, okay, this stuff, whatever data has been sent, it has been encrypted with the shared key between the CPT and GPT.
I
The
think
same shared key will be used by the remote. I think like what they have done is, uh, when the TLS connection is established between the remote user and the CPUT, the shared key that is used, instead of generating their own shared key, the shared key which is already created between the CPUT and GPT, that's the one that has been passed to the TLS protocol.
it's not that easy, Sridhar, because the way the shared key in TLS is generated uses the nonce or a random key from both the client and the server. So what they have to do, they're still playing with the TLS handshake, but rather than they're simultaneously establishing TLS on both sides, and kind of the service secret, they are kind of sharing it. Like what I'm saying is,
They had to modify a lot of
yeah,
code.
they have to modify the TLS in some way that they will end up using the same shared secret data encryption key between the two TCP, two TLS hands. So they sit in the middle, do a TLS handshake in a way that the nonce that is coming from one is passed to the other. What I'm saying is the server. So when they do the shared secret generation at the last step of the TLS, they will have to pass the the master secret it got from the one end and pass it to the other end. So they kind of play the middleman right in the middle and end up, but thereby ending up with a common shared secret, and that's what they use for the TLS. Then they
Yeah,
can. Yeah, then when the TLS data comes, they don't have to decrypt. They blindly send it to the other side because the other guy has the same shared secret.
yeah. I think like they implemented the shared key passing using DH as well as this public private key. So they have like those two options. Like one of those options they end up using
Yeah.
depending on what is supported by the remote user. So like, see, the reason is like there is a GPU driver which is running in the CPU-T. That is the NVIDIA's GPU driver. So that they don't have access. They don't publish it outside, even though it is running in Linux. So the GPU, yeah, whether it is running in Linux or in Windows, I think in this case they ended up using the Linux flavor. So they developed their own stuff. But I think like NVIDIA does not reveal the source code of that GPU driver, or like tinkering with that GPU driver. They don't allow that stuff. So how they have implemented,
So
yeah.
if they're writing their code on the outside in a user driver, are they able to get that data, the secret that's generated into the T, the
Oh
transistor?
yeah. I think like that like they were. I think they have that whatever the hooks that they are needed, they have access to that. Yeah.
Okay, okay.
Yeah, I think like a lot of time was spent in implementing this protocol, because like, yeah, it would have been, I think like the whole purpose is like, if NVIDIA sees this article, so they can this paper, so they can make changes into their NVIDIA driver and implement this whole stuff, so that like there is no need of establishing double keys and all this stuff.
Okay.
Okay. So yeah, so I think secure this server computation flow with direct communication. Yeah, here like, yeah, I think as I was telling, like the data is sent to the GPU by encrypting with the shared key, and it decrypts it. Okay, and
How does this work in the training time? What you showed for the inference, right?
so I showed like training as well as inferencing. I will be
So the
showing.
double encryption happens in training as well? The double,
Yeah, I think like I think like it's kind of like, it doesn't happen like if the data is already loaded into the.
yeah, that's what I'm thinking.
Yeah.
Okay.
Yeah. So the other one is like they found out inefficiency with respect to this double encryption, double decryption. Okay. So the other one is like, as I was mentioning, the Mac generation. It was
Serial operating.
sequential. Yeah. So what they have done is like they have what they found out is like to take advantage of the parallelism that is available in the GPUs, okay, GPU cores like the CUDA or the Tensor. So they have split the input into multiple chunks. I think like they are splitting up to 16. In this diagram, it shows 3, but like they were chunking up to 16. So like each chunk, what they do is like they add a number, okay, to this AAD kind of stuff, and then like it is fed into this GMAC, like where like this operation is done and it generates a new MAC, okay. For each chunk, there is a unique MAC, and like when it so like chunk 2 will have its own MAC, chunk 3. So even if the packets go out of order, this number will take the receiving side, the GPU will know, will reorder the packets. It knows, like it keeps an eye on this stuff. Okay, so they had to modify, they implemented this protocol, this whole stuff. They had to do it. This was another interesting thing that they did. So like with this, like when the chunk comes to the receiving side on the GPU, so like once they decrypt it, like yeah, they do all this stuff can be parallelized, all this. So 16. So a single image will be split into 16 chunks.
And on the InfiniBand, right? So,
No, it has nothing to do with InfiniBand. This is like the CPU T, see like CPU T to GPU T. So like, from the user itself, like once the
okay.
user and the GPT have established that
On the PCIe, and looking at the
communication.
transport on the PCIe, right?
Yeah, this one, no. So the
On the
user,
second secure channel on the PCIe.
this one, no, not even PCI. Like this guy himself will chunk into 16. Each image is split into 16, and he will send it to the CPU, GPU T, and that one will go through the CPU T. CPU will do just do a pass through. It will not do anything. So that's another plus point. So then, like the receiving
I'm really
side, like
confused on the protocol side, because one is the first one, secure tunnel remote user is a standard TCP IP transport.
yeah.
That there's no the MAC layer. The second one is a more of a MAC second level of authentication, is a MAC like authentication. What you're doing is, what you're asking is to do the data encryption, just to be ready for the second the MAC authentication.
For the data integrity, they have the MAC, like multiple MACs. Instead of single MAC, they're using multiple 16 MACs for each image.
Got it.
So
So
then
that
like,
becomes
can
changed to
execute
the client-side protocol. Yeah, it's a complete lot of protocol changes, right? That's what I'm.
Oh yeah. They had to develop. They developed this stuff.
So there's a TLS protocol change on the client side. There's a TLS protocol change on the server side. Okay, quite a lot of
I think
changes.
like see like so I think like the AES
Yeah.
like the Mac, that's the one that they made change. See, they're still using that AES, okay?
No, I'm more worried
Instead of,
about the TLS protocol change, right? So the TLS changes, I was trying to hoping they could minimize it, but the way they have done it, it looks like there's a TLS protocol underneath that thing has to change how they chunk the packet.
that for the direct communication part, they made changes. But for the second step, okay, for the Mac, so like all they're doing is they modified in such a way that the remote user will chunk it, and it will go each.
Yeah, that's a protocol change.
No, I think like they did it a little bit earlier, like before like sending the original packet, like they are splitting that packet into 16 chunks.
Got it. I got it what they're trying to do, but
yeah.
just that the changes is what concerns me. Okay.
Yeah. Okay. So now like server computation flow with all optimization from Fastrack. Okay. Here like you see the AES stuff like the PCI transfer and like the computation part. Okay. So this is a batch 1 and like batch 2 here you see the AES like the decryption. See like the computation is going on, so they don't have to see like what they say is like the decryption, the key that is generated, okay, the key that is used. So like uh, it can be done parallelly with the computation, and also this authentication part. So I think if you look at that sequential part, like I think like if it has to rely on the previous step, so like I think like they are going to see this one will be executed for the previous batch. They don't have to. Previously they were all doing it this stuff sequentially. Now they are going to do this other, because like they will do the computational. If anything, like if the received packet is already uh, uh, malformed, okay, then they'll drop this computation and send it to the end user. Hey, like we did not receive the right packet, it is already tampered. But most of the time it is going to be rock solid, no changes. So that's why like they are delaying this authentication stuff. I think while this stuff, I think once the decryption is done, like immediately the computation will kick in. Okay, but the authentication part, they can wait. Like once it gets a green signal, then like the computation does take time, no, especially for ResNet or some of these operations. So they can continue that as soon as the decryption is done, like the GPU computation kicks in, and the authentication can be done later for the previous batch.
So in other words, what you're saying, Sridhar, if I got that word, is there'll be some checksum calculations before the computation happens. If the checksum is accurate, then the computation will kick in. Is that what you're trying to say?
No, the computation will kick in as soon as the decryption
Yeah,
is.
you think they're doing the authentication in parallel to the
It will
computation.
not wait for the authentication to complete. It will continue. It's
Okay,
a,
so
You roll back if needed or reported error, right? So if the
but if
computer waits.
the authentication reports that okay, it is not correct, then like it will stop, and then like it will inform to the end user saying that it did not receive the uh, correct
So
data.
there's no then that is
I
no
see.
there's no danger, because what happens is that means all your computation you've done so far becomes a waste, right? Because if you're done training, let's say you might have corrupted or you poisoned your training because you're already processing some unauthenticated data. That's not a good thing, right?
Yeah, but I think like chances of that happening are slim. But yeah, if it happens, then only that part of the stuff, like it will have
No, the reason
retry.
for that, yeah, the reason for authentication is that the malformed data could be a poison, and you don't want to do the touch it if it is not validated, right? Right
Yeah, I
now,
think like probably.
optimistically operating on it and poisoning your current workflow is a little risky, I think, from a security perspective. Have they done a security evaluation of this?
No, I have no idea. Like, no, I
Okay.
think, but like, I think like what they will do is like, they will ask the end user to send the data back again. Because like for inferencing model, what's the big deal?
Yeah, but that's not usually that's not a problem, because you're not going to process the data. But here they process the data and report an error, or sending it back. That means you already operated with the poison data. That's not a good thing. It's my concern. But I would like to, yeah, that's that anyway, just a feedback.
Yeah, I can check with them. Like if they,
Yeah, check
the
it.
thing is like, yeah, if the prompt request, let's say, like I'm just giving an example, if it is already poisoned, like as a request, okay.
Okay, so you're saying the prompt case it's okay, you're saying.
Yeah, it's like inferencing, no? It will say, hey, like send the request
Okay.
again. I don't understand.
Well, so it's only inferencing is okay, but the training it's a problem. Yeah.
Yeah, for training also I can check like so
Okay.
how like I think like so like I think like they will delete it, and again like they will ask the CPUT to send the same packet back, because like they did not integrate that resulting stuff into.
That could have in play. That could have some, yeah, I could send a biased data, all that, and then several times, and then later on send this good data. Then I can queue your
No,
training
no, they
model.
will not integrate. Okay, they will not integrate. The resulting data of the GPU will be integrated into the existing model only after the authentication is.
That's the thing. That's the line I was looking
That's
for.
what they are going to do. Only
Okay,
after the
that's
authentication is
then it's good.
approved, then only they will integrate. Otherwise, they will not integrate.
Okay, but then they may have to restart that training part again. That's
Only
something.
that part only, no? Just I think they will ask the
Okay.
CPUT to send it back again. It will be a small chunk, no? Small chunk of data. It's not like big.
Okay.
Okay, so let's come to the evaluation. I think, yeah, I think like if you look at like the inferencing, you saw like the GCN like 50 milliseconds. I think these are the numbers. I think like let's go to the next slide. That will be the interesting one. Okay, so here you see this is a baseline for the GCN inference. So for direct communication, where like they cut down like one decryption, one encryption in the transmit and so they got like just hold on. Yeah, so you see like almost like 52%. Just 1 minute. So let me. Do you see this now?
I see that. I think they're trying to understand.
Yeah, the 52.8%. Okay, this is a reduction in time. So like just only the direct communication. Okay, where like they are they have implemented that new protocol which does direct communication between the end user and the uh, GPU T. Okay, they got now the work is getting done in 22 milliseconds, which is kind of 52.8% reduction. It was close to 50 milliseconds. Now it is showing 22 milliseconds. Okay, if you look at the ResNet, okay, it was close to 18 milliseconds. Now it is probably like 14 millisecond. Not much. Yeah, they got like 25.2% improvement. Okay, basically like a reduction in time. If you look at T tower, huge one, like similar to what was seen with the GCN. Okay, so it was like 82 milliseconds. Now it is like 40 milliseconds, close to 40 milliseconds. So they got like almost, I think it's less than 40 milliseconds, maybe 38 or something. So 52.1. Okay, so that's the reduction they got. This was in the inferencing case.
What are the other things? DC,
Yeah,
the
this
pipe.
multi-channel, the multi-chain one. Okay, so you see like 25.9, 25.4 reduction. Okay, for the GCL. So here, like you see less. There is nothing. If you are only using the multi-chaining, not like the direct communication, then you are only getting 5.4% reduction in the multi-chaining stuff. Whereas like with T tower, like they got 23.9% reduction. So now like this piping, where like they were clubbing that decryption stuff, the decryption like where they are efficiently while the PCI bus was transmitting and like the computation was going on, the authentication part and all that. So there they got like 12.9% reduction. And like in the ResNet only 2%, nothing much. And like with this like 8.7%. Okay, so like now like MC plus pipe. Okay, these two together like they got 31.7% and like 6.2% in the ResNet case and 29.6% reduction when they use MC plus pipe. When they combine all these three, okay, DC plus MC plus pipe, they got 84.6% reduction compared to the baseline, okay. And this number is same as almost when the NVIDIA's the confidential computing is not even being used. It is a huge, they are pretty much comparable. When like NVIDIA's confidential computing is enabled, okay, this is all like related to the Fastrack. When like because they don't have a way to modify the GPU driver and the GPU kernel and all that stuff. This is the amount of time it takes, 80 milliseconds, to do the same operation. Okay, the inferencing operation. With the Fastrack, they're able to get it done in 7-8 milliseconds, which is 84.6% compared to this one. And this is comparable to this too, the CC off. Now, yeah, with ResNet, yeah, like 18 milliseconds for the baseline with all these three. they're able to get 31.4% reduction, which is like around like 14 or something. Okay. And this is same as the CC off, which is better than the NVIDIA's CC on option. Okay. So like you might have, yeah, I think like these guys have implemented their own protocol and all. I think like the baseline, they did it on their own without using the T. Okay. So this one you can compare with this, like this is better, like whatever they have done, like without using the NVIDIA's CC on. Okay, so same thing, like here you see like 81.7% reduction time for the T tower compared to the 80. Okay, this is also kind of comparable with CC off. So when it comes to training, you see like the reduction you see in GCN as well as good reduction. Okay, 32, I think in each of them, and then like the T tower. Okay, you see a good reduction, and like here overall, like you see 55.7% reduction in time, and like in the GCN you get 72.5 reduction in time. Yeah, I think like as I was telling ResNet, we don't get much because like good amount of time is spent in the GPU processing, images are involved and all that. They got only 8% reduction in the latency. Okay. So any questions you guys have
I have
on
a
this?
question, Sridhar, one thing there on that last one, just so I understand the picture and specifically what I'm trying to understand is the combination of DC, MC pipe, MC plus pipe, and the combined, taking into account the CC on or CC off, like, you're taking those combinations.
Yeah,
So
CC on will be there. CC on will be there.
So if my reading is correct when I'm seeing here, I'll just take one example. Let's take the TT tower inference where you
Yeah.
put the, right?
Yeah.
So the way to read this is when with the combined 81.7%, you see reduction of that or savings is when CC is off, correct?
CC is on. CC is on. T, this is using T.
Yeah.
But
T,
when the
Sum of
CC
all the yellows, right? This.
But when the CC is on, I see it going up way to
But
100
Yeah,
milliseconds.
but
CC
like,
and the TEE seems like, two different things, because the first thing that's, the orange and the red is basically the TEE, which is basically the encryption keys that are needed between the different types of the pipelines are online, while CC on and CC off is a different thing with, it seems like it's a different thing with those encryption keys. That's a proprietary service, or at least that's my understanding.
yeah. So like this one is the software that they developed without you. Yeah, the Fastrack is not yet enabled. Okay, they just developed their software. Okay, like but like this one, the Fastrack is being used in these ones. Okay, so like the red, this
So,
the
a little confusing that the first blue line is confusing. The baseline that they have is that are they using CC or not using CC?
I
so
don't think they're using CC. They're using basically the
yeah, so the
TE
baseline.
encryptions.
So baseline, they will use the CC on.
So, but why is it then not equal to the light blue?
Yeah,
Their
because
base,
no. The reason is like they have developed their own software. There are a lot of stuff like see like the emulation software is part of the baseline.
no, I understand. What performance wise, I would think that their baseline, if they're not done taken any optimization into account, then their baseline should be equal to similar to what.
They don't have access to the GPU driver code, no, from
So
NVIDIA.
you think GPU driver code is slower than their
Yeah.
Exactly.
That's
So
what.
that's why I was thinking when Dimitri was said, I think the baseline that is there is with default CC on, that
Yeah.
means that I don't know the predefined security keys or what have you there for the drivers is with that is what it shows 81 or 82 milliseconds.
Yeah, yeah,
correct?
yeah.
Yeah,
So
and the baseline is
this
confusing.
is,
Like,
yeah,
what they call
compare this
baseline.
guy with this, okay? So here
Right.
it is like almost like 99 and they, so basically whatever code they have written is efficient than like the NVIDIA's code.
Ah, that's what the puzzling, right?
Yeah.
They've done
Then
something.
they are saying if they get access to this code, they can even cut it down even more.
I see that's the part I was just funny when I was
They are
laughing at that.
brilliant guys. These guys are brilliant guys.
So my question to you is, when did they write this paper?
Well, just this published like few weeks back. They worked on this
Okay,
paper for
the
almost 9
second
months.
concern, the question I have is, second question I have is did they talk to the do they do assume that on the client in the case of inference case they assume that on the client side also they have did they make any assumptions on the user side? There could be any it could be any CPU. They don't have to, right, in the picture that you have.
No, anything can be there on the
Okay,
user.
as long as the protocol can be modified, it could be anybody.
Yeah.
So the real way that this has to be done is then the TLS this has to be a TLS extension they have to ask for, and then they will have to. It could be even transparent. The TLS client.
Yeah, I think like the end user doesn't even.
Yeah, if
all
you
this
can
stuff.
make the thing
Everything,
transparent to the end
all the
user, I think the
modifications.
reason initially I thought like that, but then they were doing some things in the protocol that them look
Yeah.
like the transparency cannot be
All,
maintained. I double
all,
check the paper.
yeah, they made modification only on the CPU T side also, only, that's all. To make this stuff work.
Okay, I think this is interesting. You're given a lot of input. That is good to go and study the paper again. So it's
Yeah.
very interesting.
I
Thanks.
also keep learning new, like each time I
Right.
read like
So see that one question there. Even when the confidentiality computing is off, that still the fast track is on, right? It's orthogonal to CC off, correct?
No, yeah. This is like they're just comparing like how much time. See, like if no security is used, no T is used, okay, how much time it takes for a T tower inference? It takes like 7 or 8 milliseconds, okay. Now, like when they use the T, okay, even with the fast track, they are getting the same numbers as the.
Yeah, okay. Now
So,
it makes sense.
it's really a question. In the industry today, how often is CC turned on?
Oh yeah, I think like the financial customers, I
default,
heard
right?
that the financial customers use the CC on.
Yeah.
Financial customers and like
Both in inference and in training.
yeah, I think
I
like
would
they have
presume
to
so.
use, they have to comply. The healthcare company
Yes, regulations.
to be
So there is
compliant. Yeah.
some specification or certification or some standard that demands CC should be turned on all the time.
Yeah, I think like they have to be in compliance. They have to be on. Yeah.
No, so I'll tell you one thing, Shankar. Normally in the cloud group, right, there's a FIPS 142 that on the hardware acceleration side, where all these keys are exchanged. So that has to be there on the training side also, on the inference side, both.
Okay, so we call FIPS 142.
Yeah, just look up FIPS.
No, I know 140-2. I know
Yeah,
140.
there are 4 or 5 levels in that.
But I understand that, but I didn't know I'm more there's a de facto use of that is how much common it is now, and you're saying that more and more CC turned on is happening.
Yeah, especially in those industries, in those verticals.
Financials, yes.
Yeah, so I think like see like even NVIDIA did not come up with this feature. Okay, only the CPU Ts were there for a long
So
time.
only which CPU version of NVIDIA is having that? You earlier mentioned that H100,
H100, H200, all the Hopper architecture and the Blackwell architecture, they are supporting the CC on. The prior to that, like they don't support.
Okay, got it. Got it. But if there is any paper that certification or standard or NIST standard that says how CC should be turned on in the for the AI models training or inference, if you guys can point that to me, that'll be great. Yeah, I'll look for that. Yeah, I'll look. I'm curious to see that.
Okay.
So one question I have just on orthogonal to this one, like I think at some point you mentioned in your talk that um, there is a market that you know Broadcom and others with XPUs and all that AI on the edge that you're mentioning. So is it accurate or is still fuzzy? Meaning that you can train a model on let's say on a GPU, which let's say you need to have 400 gigs or 800 gigs Black Hopper or what have you. You train that, but then when you put it on the inference side, then you don't have to put it on the same NVIDIA's GPUs, but you can
Oh,
get
no. I think like we don't need
you
that
can
kind
put it
of
on a different vendor's thing. Well, let me just so I understand. You can put it on a different server, like from Broadcom or Dell, and then you can do inference on that. So can you do that, or it has to be the same?
Yeah.
You can.
That's the beauty, no? Like, see, if you go to any of this, like if you Hugging Face, you can download some of those models. Okay, Llama. Like if you look at Llama,
Download
you
the
can run
parameters.
Llama on your laptop. Laptop is like let's say if you have a Mac, okay, you are running on MacBook on processor.
M chip,
Okay?
M1 chip or whatever chip.
As long as you see, like you have to pick uh, the lower one, like 7 billion parameters. So probably it needs
Get
like
the weights and the
it, it-
parameters.
yeah,
The
it
weights and the
needs like
parameters for the model you have to
and like
get. That's the
2
training
gig.
data.
Yeah. So you need to have sufficient memory, and like then like when you're downloading, it also asks like you what kind of quantization you want. Okay. So if it is 4-bit, then it shrinks the size of the file even smaller. But only thing is like you may not get the best result. But like for testing purposes, you can always use. But in general, like they shrink the size when they are putting it in production inferencing part like the edge. So Meta is building up huge farms for the edge computing. Because like they don't want like uh, they want all their user requests to be handled by the edge servers.
Hmm.
And like now NVIDIA is also competing in that space, coming up with low-end uh, GPUs, which can be used in the inferencing place. Startups are also coming up in that space because there is a opportunity for all of them to play in that area.
Right. Interesting. A lot of interesting things happening here. Yep.
Yeah.
Because I was concerned more on the accuracy and the bias aspect, because if you're training on one and you're inferencing on the other.
Shouldn't matter. As long as the model and the weights are maintained, weights parameters are maintained, you should be get the same result, right?
No, but it should, but if the standards are not maintained or whatever the protocol is not, you will have different results, is my thing. Because
No,
if you're doing on if you're training on, let's say, large sets on your servers, and now you're deploying on an Android device, the result will be different, like, with quantization, but the accuracy will vary, right?
Yeah, I think like what even like Apple, like the iPhone device, like I think like this they call it as artificial or like intelligence. I don't know whatever the product name they call it as. Like they are tied up with OpenAI.
Right.
What I'm hearing is so like there is a new I think like a NPU. So there is a processing unit in the ARM chip which does the local processing. So basic stuff like it can answer quickly. If it cannot get the answer, then like it will connect to backend server where additional processing is done and then it gets the results back to you. So yeah, the ARM processor today, like in the iPhones, they have like this inferencing related chip, the co-processor chip or whatever you call it as. But I think those are getting more and more powerful. But I think this is like a small case, but in general, like there is opportunity for all the guys in the edge place.
So you're saying this is some kind of a hierarchical approach where they can do some initial basic things in the hands, and then if they're not, you go to the edge AI, edge servers, and that has more compute.
Yeah.
Yeah, that would be good to see some details around that, right? Yeah. That's great. Yeah, but this paper was interesting, very interesting. Thanks for reading it out. Yeah.
Yeah, yeah. So I did not go, I think I did not read. I think I took diagrams.
No, now it becomes easier to read with your input,
Yeah.
right?
Yeah,
Thanks.
yeah.
No, this
So-
is really wonderful, Sridhar. Thank you.
Thanks for the time and effort taken to do it.
Yeah. Any other questions, guys?